I'm Melanie, and I'm going to talk about how I developed a new prefetching algorithm for Postgres over the past few months using a simulator, and then I'm going to talk about a little bit about the actual algorithm itself. So first of all, what's prefetching? It's any time that data or instructions are fetched preemptively to cover perceived latency. So that can be cache prefetching, it can be storage prefetching. We're going to focus on storage. I'm focused on storage prefetching, and storage prefetching can be done by the operating system, or it can be done by the application. When it's done by the operating system, it's normally called buffered I/O, and there's different reasons why applications might want to do storage prefetching themselves, but of course it's a lot of additional work, so there has to be a good reason. So an application will only do its own storage prefetching if it does enough I/O, it's I/O bound frequently enough that it matters, and it's performance sensitive. But also, importantly, it has to have something to base that prefetching on. So it has to have some superior knowledge of its data access pattern over and above what the kernel has. So an example of that would be a web browser that's doing content-directed prefetching. You search for something, and the search results, the next thing that's requested of a web server is going to be at one of those links. You're not going to click on something that's not in the search results, right? So the browser can issue prefetch requests for resources that are linked in those links. There are different kinds of prefetching. There's irregular access prefetching, which might be different files, different blocks in different files, like imagine an index scan. And there's sequential prefetching, which is the simplest kind. It's just a process needs the blocks in a file basically in order. And it seems simple enough, so why not just get literally all of the blocks, just request all of them? And the reason is that you need to balance competing needs. This query might not be the only query on the system at that time. And the query might not need all of the blocks in the file. So requesting all of them wastes resources unnecessarily. And you want to make sure that you're balancing those two competing needs. So a good prefetching algorithm will balance timeliness and limited waiting for the client with keeping the resource use as low as possible so that the device and memory can be used for other tasks and workloads. So prefetching is already in limited use in Postgres, and basically we're talking about, bitmap heap scan, recovery is another example, and existing prefetching in Postgres, because it uses buffered I/O, is using some operating system facility to inform the operating system, hey, I think I'm going to need these blocks, so like fadvice in Linux. But we have to implement real prefetching as if we want to implement direct I/O in Postgres. And the proposed asynchronous I/O patch set includes direct I/O. And asynchronous and direct I/O in Postgres is going to lead to a lot of performance benefits, but it also means that Postgres has to do its own storage prefetching at that point. There is an existing prefetch algorithm in the AIO DIO branch in the proposed patch set, and it's loosely based off of the prefetch algorithm that's already in Postgres, which is just using sort of prefetch a little at the beginning and then maybe double the prefetch distance as you go, and using a constant multiplier. And this is not ideal for a lot of reasons, but I think primarily it's not adaptive. So changes in the available storage resources, changes in the needs of the consumer are not taken into account. So it's going to do what it's going to do regardless. Developing the prefetching algorithm using real storage and real workloads is challenging. It takes a long time to run a benchmark and actually get to the part that's exercising a prefetching algorithm. You have to design everything perfectly. You have to configure Postgres, the file system, the operating system, all of it, so that it actually puts under test what you're trying to test. And then once you find something that you would like to investigate further and see if it's an effect of the algorithm, you have to reproduce the whole scenario. And things aren't that reproducible. And then on top of that, think about like all of the different scenarios that we want to test. Some of them are not even things that you can really create in real life. So that might be like a sudden spike in latency or a decrease in available IOPS caused by, other tenants on a server, or, there are different types of things that are going to take a long time to reproduce when you could just simulate it. So using a simulator is faster. We can iterate quickly and also all of the scenarios, all the types of storage, all the different storage subsystems, all of the sort of situations that we want to recreate, we can do that with a simulator. And also we can be systematic. We can say we changed this one thing and then led to this change in the output, which is really hard to do on a real system. So I wrote a simulator in Python that uses the abstraction of a pipeline with different buckets, I call them. And the buckets represent different states that an IO can be in. And each bucket has mechanics that govern how IOs are moved from one bucket to another. And it abstracts away time with the concept of ticks. And this means we can fast forward through periods of time where nothing is happening and then like focus in on times where a lot is happening and simulate long-running workloads and different mechanics of different storage systems. The steps of my development process using the simulator are to model the storage system, model the workload, then experiment with the prefetch algorithm and look at the data. I'm going to use IOU-ring as the example to walk through how I went about modeling the storage. IOU-ring is a relatively new async syscall facility in Linux, and a submission and completion ring buffer are mapped into user space. And processes can write submission entries into one and read completion entries from the other. There's a variety of options for configuration, but one of the important mechanics is that there's a fixed number of buffers, which effectively limits the number of in-flight IOs at a given time. Also, syscalls can be amortized across many IOs. And then when you actually do the submission, there's some submission overhead. So in my simulator, I simulate that submission overhead. I simulate that batch submission, and I simulate that limited ring size. And all of this is just the submission process. Once IOs are submitted to storage, then they're being moved from being in flight to being completed at a rate. And so like based on the storage specs, the IOPS, the bandwidth limitations, that's the rate at which they're completed. And so I've simulated that using latency and max IOPS, and it's a user-defined latency function, and then you specify the max IOPS, and IOs will be guaranteed to remain in this bucket until at least the latency as specified by the latency function is passed. But as more IOs than can over and above max IOPS are submitted, the latency will increase pretty much linearly of IOs that are submitted after that or dispatched after that to storage to when they actually complete. And the latency function is, again, it's the amount of time that an IO must spend in these buckets that simulate storage. Now, the next step is to model the workload. So we have modeled our storage, and when we model the workload, you basically just define a consumption rate. That's because from the perspective of designing a prefetcher, it doesn't matter what else happens in a query or for a maintenance process. All that matters is the request rate, the rate at which it's requesting IOs. So the consumption rate can be constant, it can be changing, it can be like randomly changing. You can model it however you want. And the point is to kind of think about an actual workload that you'd want to model from a benchmark or something like that. The next step is prefetch algorithm development. In order to experiment with the given algorithm, you specify a prefetch rate, which is how many IOs you would like to prefetch and at what intervals or frequency, which makes up the prefetch rate. The prefetch bucket will then move IOs at this rate into the subsequent bucket. When evaluating output from the simulator, we have to first define what good and bad look like. Good for a single result is minimal excess buffers are occupied. Waiting on the part of the consumer is as little as possible, and as few extra IOs are requested as possible. And importantly, the latency is as close to the base latency as possible. So we don't put more IOs in flight than the storage can handle, which would increase latency. On the other hand, thinking about what bad looks like for a prefetch algorithm, take the example of storage being the bottleneck. When you have slow storage and the prefetcher is too aggressive, you'll see latency increasing over time and diverging from the base latency. And you'll see a pretty consistent number of in-flight IOs because it's already basically bumped up against max IOPS. But there'll be no IOs that are completed and not consumed because the consumer is picking them up as soon as they're finished. On the other hand, if the consumer is the bottleneck, you won't see latency diverge much from base latency if the storage can easily handle that number of IOs. But you will see the number of buffers being taken up by unconsumed IO that's completed growing, which is also not desirable because it takes up unnecessary memory and uses storage resources that are not needed. In order to evaluate our results, we want to compare them to baselines. There are two ends of the spectrum. On the one hand, we have the synchronous baseline, which is the IO performance of a workload if there was no prefetching, if all IO was requested on demand. And with synchronous IO, fully synchronous IO, every IO will incur the full storage latency. And you can see in this example that the query or the IO that's requested takes about 100 milliseconds. On the other end of the spectrum is the extreme case where all of the IO that's needed is requested at the beginning. And in this case, you can see that for the fetch all baseline, it takes about 40 milliseconds. But what's happening is that since all of the IO are requested and they're finishing faster than the consumer can consume them, the number of completed not consumed buffers is growing, and you end up taking up many completed not consumed, many buffers with completed not consumed IO. You want to land in the middle. So a feedback directed prefetcher would adjust the prefetch rate such that the number of completed not consumed buffers is maintained at a low level equal to some headroom value, but we're able to still complete the query in the similar amount of time as the fetch all baseline. So the consumer isn't waiting because there's always IO that's completed in time. So what we're actually looking for with the feedback adjusted prefetcher is for it to be one size fits all. We want it to work for different storage speeds, different consumption rates, changes in consumption rates, and adapt to them without any configuration by the user. And the challenging part about this is that we want to do it with feedback only, because we don't have the ability to introspect the storage or to know exactly what the workloads are going to do. So we have to make it both adapt and also be versatile enough to work with all of these different types of storage and workloads. So what's the challenge in adjusting to different storage types? Cloud storage and local storage typically present in very different ways. They have very different latency and very different IOPS limits. If you have a fast local NVMe drive, you'll often get sequential read latency of 500 microseconds and up to 1 million IOPS or more. And with cloud storage, typically you'll get sequential read latency around 3 milliseconds, and you'll likely not be willing to pay for more or even be able to find more than 20,000 IOPS. So the prefetcher has to adapt. So it has to accommodate different types of storage. So those are the limitations out of the gate. But it also has to adapt when the workload changes or the available storage resources change because another workload is present or suddenly you run out of burst credits or something like that. An example of adjusting to the consumption rate is here. So the green line is the consumption rate. And you can see that it increases for a while, then decreases, and then decreases again. And we're bottlenecked on the consumption rate in this case. The max IOPS of the storage is above the consumption rate for most of the query. So you can see that the prefetch rate, when we use our adaptive prefetcher, adjusts to accommodate these changes in the consumption rate. And because we're bottlenecked on the consumption rate, you can see here that remaining IOs to prefetch and IOs that are done loosely mirror you can see the little elbows in the curves are basically when the consumption rate changes. Important thing is that the IO latency, the base latency is like 3 milliseconds. And when the consumption rate changed all of a sudden and increased, initially we had a big increase in IO latency because we prefetched a lot to make up for that change in the consumption rate. But we exceeded the storage max IOPS, which led to that increase in latency. And once we noticed that, we were able to adjust back down and eventually settle at that base latency. Also, you can see here that the number of completed not consumed buffers, we're able to maintain it right around that headroom value. So here headroom was 15, and we're trying to push up the rate to establish and maintain 15 completed not consumed IOs. And whenever there's a change, you might see a spike in the number if we slow down. The consumption rate and the prefetch rate is too high, or you might see a dip in it if we speed up, but eventually it normalizes. On the other hand, if the storage is what's changing, here you can see the orange line is max IOPS, and it suddenly shoots up because we have more available IOPS, say another query finishes or something like that. The prefetch rate is able to adjust to it. The prefetch controller that I've designed loosely models a closed loop control system informed by, so the prefetch rate is informed by feedback that's observable in the system, like say the number of IOs consumed over a period of time, and then that's used to actually determine the prefetch rate. So the IO control system that I used to design the controller doesn't look exactly like a typical diagram of a query being made in the Postgres database. We are simplifying and abstracting away actors and processes that aren't important to the process. The prefetcher doesn't really care about anything that happens until the IO is actually requested. It doesn't care if the requester is a maintenance process, or it's a user query, or it's, some of the blocks were in shared buffers already. All it cares about is the IOs that are actually requested. And the consumer box here represents, any consumer. It doesn't matter if it's a, worker doing vacuum, or it's a client issuing a query. It's going to request the IOs and consume the IOs. Feedback adjusted control systems are a big part of everyday life. If you're driving a car, there is actually an equation that you could use to determine the angle of depression of the accelerator that would help you to attain your desired speed. But no one drives like that. You look at the speedometer and you depress the accelerator a certain amount, and then you let off the gas or press the gas down more based on the speedometer and your knowledge of how driving works and how long it takes to get up to speed for your particular car. And of course, different cars have different capabilities and max speeds and accelerations. And cruise control most cruise controls rely on basically a PID controller, which is probably the most common type of feedback adjusted controller. In the I/O control system, similarly, we could, if we had access to the exact max IOPS of the system, the storage system and the throughput and bandwidth, and we knew the desired consumption rate of the consumer, calculate the perfect prefetch rate. But the problem is, not only do we not have access to those pieces of information, but it's not interesting because they change. So there are disturbances and changes in the system, and you run out of burst credits, or another query starts, or vacuum starts up, or auto vacuum starts up, or something happens that leads the system resources to change. And you don't want your prefetch rate that you perfectly calculated and determined when there are no other queries running on the system to be the same rate that you use when there's other activity, or, some workloads may require a lot of I/O at first, and then their I/O becomes more intermittent, or they might have an intermittent pattern with bursts of required I/O, like a nested loop join with a really computationally intensive inner side or something like that. So ideally, you want to be able to use the outcome of having done prefetching in the past to actually adjust your prefetch rate now. The types of feedback that we can use to adjust the control system are things that are observable and that we can gather during the normal course of running the database. So these are things like the number of IOs in flight at a given time and the latency of a given IO, the number of IOs that are completed but not yet consumed, and importantly, the number of IOs that are completed cannot exceed how many you've submitted. So the demand rate, or the sort of actual consumption rate, is going to be the minimum of how much IO the consumer wants to consume, the desired consumption rate, and what the system can actually do, the max IOPS. As I think about the prefetch controller algorithm, it's important to have opposing forces so that the prefetcher can adjust up and down. So locally, the prefetcher wants to adjust for the goals of an individual workload and meet the demands of that workload and the demand rate. However, as it does this, whenever the prefetcher is too aggressive, there's going to be accrued error. There's going to be IOs that are in flight in excess of what the system can handle. And even if you maintain the correct prefetch rate for your demand rate, you won't be able to pay down that debt of accrued in-flight IOs unless you adjust for that too. And that negatively affects concurrent workloads. So the prefetch algorithm that I arrived at so far is kind of 3 parts and has to do with these opposing forces. It uses the demand rate, which I am measuring by counting the number of IOs consumed and the duration over which they're consumed to estimate the demand rate. And you take that and the old prefetch rate, and your goal is to sort of adjust the demand rate or the prefetch rate to the demand rate. And the second part has to do with the number of completed, not consumed IOs, and you want to keep at least headroom number of those around. And then finally, you have to correct for that accrued latency that I discussed. So let's deep dive in a little bit to step 1. So this is about adjusting the prefetch rate using a demand rate. This is really the crux of the prefetch algorithm. When IOs are consumed by the consumer, it takes the time between giving consumptions and calculates a demand rate. And this is usually used to decrease the prefetch rate. So the thing to note about this is that the demand rate can't exceed the highest prefetch rate that you've ever set. So if the storage is super fast local storage and you've set the prefetch rate pretty low to begin with, using just the demand rate to drive the demand rate minus the prefetch rate to 0 is only going to be so helpful, because you're not going to be able to increase the prefetch rate to take advantage of the extra storage, because more IOs are not going to complete than that you already submitted. So that's where step 2 comes into play. So you set a headroom value. This is the number of IOs that you want to have completed but not yet consumed, so that you have wiggle room if something changes and you need time to increase or decrease the prefetch rate accordingly. And so having this goal of having X number, headroom number of IOs completed but not yet consumed allows you to increase the prefetch rate in order to drive completed not consumed IOs minus headroom to 0. So if you start the prefetch rate lower than the consumption rate and the storage rate, you will never be able to get completed not consumed IOs to the headroom value, because the consumer will just pick them up and pick them up and pick them up. And so you'll continue to increase the prefetch rate to try to meet this goal. The result of using these 2 steps is pretty good. So you have the demand rate and the completed not consumed controller, and you can see the purple line. We basically have the prefetch rate just above the demand rate, and that delta that you see represents the headroom, trying to keep the headroom value. In this example, the max IOPS of the storage is the bottleneck. So we're not able to do more than a certain, the consumption rate, the consumer is always going to be waiting because it's higher than the max IOPS of the storage. But the problem with keeping the prefetch rate just slightly above max IOPS all of the time is that you're going to accrue slowly over time excess in-flight IOs over and above what the storage can handle, and that is going to cause the latency of each IO to go up over time. So you need an opposing force which will correct for that error of the increase in the prefetch rate due to the trying to meet the headroom value. The third step in the controller is an effort to do this. So it uses latency and attempts to drive the rate of change of the latency to 0 and reach a consistent base latency. And this is to correct the error caused by the headroom adjustment. You can see by the purple line on the chart that we're able to get the prefetch rate down below max IOPS using the rate limiter and keep from increasing the latency of each IO. And keep only the number of IOs in flight which the system can handle. And you can see in the latency graph that there's a spike in IO latency when the prefetch rate is in excess of max IOPS as it's adjusting, and then that spike decreases and we settle around base latency. There is still a problem with this design, and it's what I'm working on right now, which is that there is accrued error. So by trying to drive the latency rate of change to 0, we do end up, we can settle at a latency that is above the base latency. So we might actually end up with a prefetch rate that is at max IOPS, but while we were adjusting, or because of fluctuations in the consumption rate or max IOPS, we ended up with accrued latency, accrued error. So IOs, there's enough IOs in flight in excess of what the system can handle that even though we're prefetching at the right rate now, there's a backup in the system. And so we need to decrease the rate below what it might need to be at a steady state so that we can pay down some of that accrued error. Solving this particular aspect of the problem and improving the algorithm is the main next step. There are several other things to think about, like the starting prefetch rate and how to set that. And then I need to implement it on the AIO branch and start benchmarking. I'd also like to use the simulator for other things and get the code to a point where people can use it who are interested in it. Okay, so here's a couple links to the code for the simulator, the code for the AIO branch, and some of the resources that I use to inspire the development of the prefetch algorithm. And let me know if you have any questions. I'd love to talk more about the simulator, the algorithm, or AIO on Postgres.